Hi everyone, this is the start of Chapter 15 about exponential, logistic, and logarithmic equations. Today we're going to be looking at Section 1 on exponential and logistic functions. So we'll start with some definitions. So the first definition is that of an exponential function. And through the magic of it, and we're back. So an exponential function is a function that can be written in the form f of x equals a times b to the x, where a is non-zero and b is greater than equal to 0. Strictly greater than 0 and not equal to 1. So we call the a coefficient the initial value. That would be the value of the exponential function when x is equal to 0. And we call b the base of the exponential, where b is like the rate, I shouldn't say rate, I should say the ratio of increase. So like that's the factor for each whole number change in x. The value f of x increases by a factor of b. So exponential functions grow very, very quickly because they are multiplicative in nature, that each time you're growing by a factor of b. If we look at this, though, we can note some end behavior here. So recall that we have this property of exponents. So if we take the limit as x approaches negative infinity of our exponential, what that's going to mean is that the x is a negative number, which really means then that we're going to have like a 1 over b. And as x keeps getting bigger and bigger and bigger, the number in the denominator of our fraction is going to keep getting bigger and bigger and bigger. And as a result, our fraction is going to keep getting smaller and smaller and smaller, approaching the number 0. So what this means is that we have a horizontal asymptote for all these exponential functions. And if they're written in the form a times b to the x, then that horizontal asymptote is at 0. So a second note is just like a clarification. So if I have the function 2 times 5 to the x, that is not the same thing as 10 to the x. You cannot multiply those two things together. You're violating the order of operations. In the order of operations, we'd have to do the exponent before we can do the multiplication. So you are absolutely positively not allowed to do something like this. And it's really critically important that we have this multiplication symbol here to separate this because, well, 2 times 5 to the x is also not the same thing as like 25 to the x, right? What is okay to do instead of writing that multiplication symbol there is to write like a parenthesis. And that is okay. The next thing we're going to do is just looking at how to evaluate an exponential function. So let's say we want to evaluate the function f of x is equal to negative 2 times 4 to the x at the following values. we're going to do f of 2, f of 0, f of negative 3, f of 1/2, and f of negative 3 over 2. So to do this, I'm just going to use my calculator. So I'll do negative 2 times 4, and then I'll do the exponent button and type 2. So 32. And then we'll just go ahead and change the 2 to a 0. That gives me negative 2. We'll change that 0 to a negative 3. That gives me this value, but maybe I'd like this as a fraction. So if I press the math button and choose the fraction option, I can have that reported to me as a fraction. Let's real quick write down some of these before I forget them. All right. Next up, so I'll press alpha or second and enter twice there. Change that negative 3 to a 1/2. That gives me negative 4. And then we'll change that 1/2 to a negative 3 over 2. And that gives me a negative 0.25. Again, maybe I want that as a fraction, and I didn't recognize that that was negative 1/4. So I did that fraction command again. Is everybody okay with that? Good. That should be pretty easy. You're just kind of evaluating things, and these were probably easy enough things that you could have done those in your head even, or on a sheet of paper without even having to use your calculator. That wouldn't have been too bad. Now let's say that we wanted to write the exponential function that passes through these points. So the first thing I'm going to do is look to see if I have the x value of 0. Since I do, I know its y coordinate immediately gives me a. Again, I'm writing the exponential function, so I need something of the form a times b to the x. So I can get a straight away for free. Remember when we defined the initial value? That was the value of the function when x was 0. So every time if I'm looking for a, I just find the place where x is equal to 0, and that'll tell me a. Next, what I'm going to do is I'm going to look for a constant multiplicative factor. So I see that 3/5 times 5 gives me 3. 3 times 15 gives me 5. And 15 times 5 gives me 75. So what this tells me then is my value for b. So that's everything I need to know. So I can say f of x is equal to 3 times 5 to the x. And again, if you don't see this multiplicative factor right away, you should definitely see this one. And if you see that one, you can just use that to check the other ones, right? And you could just check on your calculator or something if it doesn't look like an easy problem in your head. So like 3/5 times 5 does give me 3. So you could figure that one out just by testing it after you get this one, which is an easy one to get. You just need to check that it does work at every step along the way. And maybe 15 times 5 isn't obviously 75 to you again. Just check it to make sure that it does work, and it does. So we're good there. Next example. So in this example, we're going to write the exponential function that passes through the points negative 348 and negative 112. So this example is a little bit tougher because we're not given that a value just basically for free because we don't have the x coordinate or the point where the x coordinate is 0. So again, we know we're looking for an exponential function. It says so in the directions. So that's what my equation is going to look like. So what I'm going to do is I'm going to write a system of two equations. So I know my value for f of x is 48, and my value for x is -3. So if I plug those in, I get one equation that says 48 is equal to a times b to the -3rd. And if I do the same thing for the second set of points, I get the equation 12 is equal to a times b to the -1. Now, if you guys recall, we have this property of exponents that I'm going to use. So what that's going to allow me to do is rewrite this as 48 equals a over b to the +3, and 12 is equal to a over b to the 1st. And then if I just multiply the first equation on both sides by b to the 3rd, I'll clear my fractions, leaving me with 48b to the 3rd is equal to a. And if in the other equation I multiply both sides by b to the 1st, I get 12b is equal to a. So if we look at these two equations, what we've done here is we've isolated each equation the a. Since each of these two equations is equal to a, I can now set them equal to each other, doing like a substitution. So that gives me this. This is a polynomial equation. So to solve this polynomial equation, it has to be equal to 0. So I'm going to subtract the 12b from both sides. And I'm going to try to solve this equation by factoring. So if I look, I notice that there is a greatest common factor of 12b. So I'm going to factor that out. That leaves me with 4b squared minus 1 is equal to 0. And if I look at 4b squared minus 1, that's a difference of 2 squares. I can factor that as well. So that's going to give me 2b minus 1 times 2b plus 1. Again, what I use there is that a squared minus b squared is equal to a plus b times a minus b. That's what I mean by difference of 2 squares. Oops, and I forgot that this is still equal to 0. Okay, so what I can do then is I apply the zero product property and set each of these equal to 0. So in the first equation, if I divide both sides by 12, I get b equals 0. In the second equation, if I add 1 to both sides and then divide both sides by 2, I get 1/2. And in the third equation, if I subtract 1 from both sides and divide both sides by 2, I get -1/2. But let me pause here for a moment. If we think back to the very beginning, when we defined what an exponential function looked like, we go all the way back here. We had these two criteria for b. The b had to be positive, that is greater than 0, and then it cannot equal 1. So let's go back and look at our results here. Well, 0 is not positive, and -1/2 isn't positive. So our only value of b that we can use here is 1/2. And now that I have this, I can go back and plug this into either of these two equations to solve for a. For the sake of argument, I'm going to use this one. So that tells me that a is 6. So my function then is 6 times 1/2 to the x. Does that feel okay? I hope so. Next up, we're going to be talking about a special base for our exponential functions. That special base is called the natural base. So the natural base, or sometimes called Euler's number. Euler was the name of the, oh boy, was he? I think he was a French mathematician that kind of developed this concept. The symbol we use to denote this special number is the letter E. So this letter E represents an irrational number. Remember, irrational numbers are those that have decimals that don't end and don't ever repeat, like the number pi. Again, we give that number 3.14, yada, 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 a symbol to represent it. We use that Greek letter pi. We're doing something similar here by using the letter E. And we chose the letter E because it's the same as the first letter of Leonhard Euler's name, the mathematician who developed these concepts. The value for E is determined by the limit as x approaches positive infinity of 1 plus 1 over x to the x. And that value is about 2.718281828, yada, yada, yada. I know it looks like there's like a repeating pattern there in the beginning, but that pattern deviates quite quickly, and it's not actually anything repeating there. Now, this natural base is a really important number because it's, hold on, my dog is attacking me. Okay, I'm back. I think the dog was getting jealous that I was talking to the computer. It was very strange. But this natural base is really important because what it's really going to do is it's going to be really useful in representing situations where a system is growing exponentially kind of continuously, or good representing a system that, you know, like has kind of continuous or uninterrupted change going on. So like if an organism is growing, that organism is growing all the time with respect to time, right? Like it might be really, you know, like unnoticeable, but like every instant, like, you know, like a baby is growing or something. Or if you have like a cup of hot water, that cup of hot water is cooling down, like the temperature in that cup of hot water is changing all the time until it gets to like room temperature. So like ideas like this, where like that change is happening all the time, it's kind of natural to use this number to deal with them. And as a result, like in the natural sciences and even the harder sciences, mathematics and physics and chemistry and biology, this is a really useful tool. And what it's going to allow us to do is develop a second definition for an exponential function where the base for our exponential function is always going to be this number e. So our second definition for an exponential function is a function that can be written in the form f of x is equal to a times e to the kx, where a and k are non-zero numbers. So this is just a second definition. It's one where the base of our exponential, though, is always going to be e. So the parameter that's going to control the rate of growth in our exponential, that's going to be this value for k. So somehow we can convert, or we'll be able to convert between these two different definitions of exponentials. And we'll do that a little bit later. We're not going to do that right this second. And I can't remember, maybe not even in the same lesson. but we'll do that soon. So what we're going to do now is we're going to classify exponential functions kind of into two classes. So those two classes are exponential growth and exponential decay. Okay, so these two classifications for exponential functions are growth and decay. So for any exponential function in the form f of x equals a times b to the x, or the equivalent form a times e to the x. And remember, just a moment ago, we said that there's a way to convert back and forth between these two forms. We're not going to do that right now, but it is possible to do that, and we are going to do that a little bit later. But you can represent the same function in either form. So these are, I wrote an equal sign between them because these are meant to be the same function. They're just written differently. So if that a value is positive and either the b is greater than 1, as in the yellow equation, or the k is greater than 0, as in the blue equation, then we will call this exponential growth. And then the second situation, again, if that a is positive, and if b is between 0 and 1, or k is, I don't know why I wrote less than 1 there, guys, less than 0, then we call this exponential decay. So there's two types, exponential growth and exponential decay. So examples of exponential growth, so compound interest, like money in the bank, grows exponentially. Like population, when the resources are good, populations tend to grow exponentially. Examples of things that are described by exponential decay. So we had the cup of cooling water. That's an example of exponential decay. So if you have a hot object in a cold room, the hot object will cool by exponential decay. If you guys have talked about half-lives and radioactive decay in your chemistry or probably even earth science class, you'll probably talk about that. So like radioactive isotopes decay, and that decay can be described exponentially with an exponential decay function. So those are, again, examples of like real things. Like these are real things that people would really want to describe and be able to predict how these things happen. And exponential functions are a great way to kind of do that. Okay, so let's look at an example problem. Given the population of a certain city in 1990 is 782,248 people, and the population of the same city in 2000 is 895,193 people, and assuming the population growth is exponential, in what year will the population reach 1 million people? So what I'm going to try to do is I'm going to start by writing an exponential equation. So I want something in the form a times b to the x, where we're going to represent f of x as the population of the city, and we're going to use x to represent the number of years after 1990. And this is pretty typical. Most exponential functions that we're going to write are going to be the independent variable, or x is going to be describing a quantity of time. And the y would be whatever it is that's kind of changing with time. And it's not hard to imagine that obviously time is the independent variable there. Like the population getting bigger or smaller isn't changing time, that the population, grows or shrinks because of time, right? Because other things, time changes and people get older or have babies or whatever. So we're going to start by writing that model, and then we're going to use that model once we've written it to figure out the year in which the population would reach 1 million people. You'll notice here that I also, for x, instead of just using x to be years or the date or something, I chose the years after 1990. Again, that's a pretty common thing to do. I'm just going to have to make sure that when I solve this for x, I remember to add it to 1990, or phrase my answer as that many years after 1990. But I'm really just doing this to keep the numbers a little bit smaller when I do my calculations. Like if I can make, instead of using 1,990, I can just use 0 for the first year. That helps quite a bit. So what I'm going to do now is I'm going to take these the information in here and translate this into points. So we have x and f of x. So from the yellow information, 1990 is 0 years after 1990, and the value for f of x is 782,248. This has the additional benefit of saying x is the years after 1990, that this value is my a. I got it for free. I didn't have to do any hard work to get it. It just happens because of the way I defined x to be. So that's another really nice benefit for choosing x to equal or to be the years after 1990 as opposed to just being the date. Now if I look at the blue information, well, 2000 is 10 years after 1990, and then my population is just 895,193. So what I'm going to do is I'm going to use this point to solve for b, because that's the piece that I still am missing, right? I know a, we found it here, still need to find b. So what I'm going to do is I'm going to plug in 895,193 equals 782,248 times b to the 10th. Everybody okay there? So to solve this, I'm just going to divide both sides by the 782,248. So 895. You know what? Let's just write that as a fraction. We're going to do this all in one step on our calculator anyways. I just have to kind of organize it so it makes sense as to what I did. So there we go. I divide both sides by the 782,000 and change. Next thing I need to do is get rid of that power of 10. So to get rid of an exponent 10, I'm going to use the 10th root. Now, ordinarily when I take the even root to both sides of an equation, it makes a plus or minus. But since we're solving for the b of an exponential, the base for this exponential, I know that the base for an exponential has to be positive, so I can just disregard the plus or minus. And that's what I'm going to do in my calculator. So the first thing I'm going to do is type the 10 for the 10th root, and then I'm going to press the math button and select option 5 that allows me to choose the kind of root that I'm going to make. And because the 10 was already there, it just sucked it up into the index of my radical. Notice that's not a coefficient anymore. It's kind of written as a superscript. And then I'm going to type the fraction in there. So I'm going to press alpha and y equals to get the fraction options. And I'm just going to choose the numerator over denominator one. So I can write just an improper fraction. And I'll just write 895,000 and change over 782,000 and change. And then we'll just press enter. So that tells me that the B value is about 1.014. But let's use the whole value here because we're dealing with an exponential. Like, all these little decimal points kind of make a big difference. So I'm gonna take all my decimals that have been given to me, and I'm gonna use a parenthesis here just so it's a little easier to kind of see what I'm doing. So I'm gonna do that. Okay. So what I want to do is I want to find the value for x when the population is 1 million. So initially, you would think, okay, well, we'll just plug in, you know, 1 million for f of x, and then solve for x. And you're like, okay, well, I'll just divide by 782,000, sure. And then we'll divide by 1.01, yada, yada, yada. And that part's way wrong. So remember that this x is in the exponent. It's not like multiplied to the 101. It's the exponent. So some of you might remember that, like, oh yeah, we had a way to do this back in our Algebra 2 class using logarithms. Well, and we'll eventually get there in this class doing that, but we're not quite ready to talk about logarithms yet. So I'm going to do this just graphically. So I'm going to go to my calculator and press my y equals button. For y1, I'm going to just type in my exponential model that I've written down here. So 782, 248 times 1.013578108 to the x. And in y2, I'm going to type in that 1 million. So 1 with 6 zeros after it. And now if I hit graph right away, I'm probably not going to see anything because, well, these are huge numbers and my window is probably set to be like -10 to +10. Yep. So I'm going to press the window button and reset my window and choose my own window. So remember, x is representing the years after 1990. So I know that the minimum years after 1990 we'd be talking about is 0, right? Time going negative doesn't really make any sense. And if it says our model is beginning in 1990, it wouldn't make any sense to consider years before that. And since we're clearly looking at a growth situation, since the value for b here is bigger than 1, there's no sense I'd be interested in any years before 1990 because the population isn't a million yet. As far as the x max goes, I know at in 2000 the population is almost 900,000. So it's got to be a number bigger than 10. I don't know how much bigger than 10. I'm going to guess and just pick 30 years. I figure after 10 years we gained about another 100,000. Another 10 years we'll probably gain another 100,000. That's not quite there, so I'll pick 10 more and that ought to do it. The y min, well, this 782,000 was the population 1990, and we're growing every year since then, so that would really be my minimum value, but I kind of like round numbers. So instead of doing that, I'm just going to pick 750,000. That's a little less than that, 782,000. And the y max, well, I know it needs to be bigger than 1 million because that's the population I'm looking for. And in the interest of round numbers, I'm going to do 1.5 million. So that's 15 with 5 zeros after it. And now I'm ready to hit graph. So this first curve coming in is the population of the city. you see that it's a pretty flat exponential curve because the growth rate here, the value for b, is awful close to 1. So that city's not growing tremendously fast. But the point that I'm interested in is the intersection of these two. This straight line is the 1 million coming on in there. So to find that intersection, I'm going to press second and the trace button. And the command I'm looking for is surprise, surprise, the intersect command. So I'll scroll down and click on that. Now you notice that the calculator has given me some questions here at the bottom, and my cursor's popped up there. So it says first curve. Well, this is one of the curves I want to find the intersection of. So anywhere on this curve, I can press enter. Where my cursor is right now, that's fine. So I'll just press enter. You notice when I did that, it automatically toggled my cursor onto the next curve, and now asks for a second curve. Well, I only had 2 curves in my calculator. The intersection I want to find is between these two, so I'm on the other one, so I'm good there. I'll press enter. And then it says guess. You don't really need to move the cursor to the spot unless there's like a bunch of intersections and you're interested in a specific one. When there's only one intersection like this, you can just press enter anywhere and it'll find it. So it says that intersection happens when x is about 18.21. And this is years after 1990. What would that mean? Oh, it would be during 2008 then. So sometime during 2008. Let's reread that question and make sure that we're answering that correctly, because sometimes we'll be specific and say like at the start of what year or something like that, and then we have to be a little bit careful. So in what year will the population reach 1 million? So during 2008, I would say, is a perfectly reasonable way of answering that question. If they said at the beginning of which year does the population exceed 1 million, there you would have to answer 1999, because when x is equal to 18, we're still not to 1 million. It happens 18 and some change. So you just have to be a little bit careful about reading the question and making sure that you understand what the question is asking for, and you answer the question that's being asked with the rounding issues. So that's okay. What we've done here. So during the year 2008, I think is a perfectly reasonable answer. If this question had said at the start of what years does the population exceed 1 million, there we would have to answer 2009, because again in 2008 we're not quite there. Okay. So next idea here, we're going to move on from talking about exponential functions to start talking about logistic functions. So let's let a, b, c, and k all be positive numbers, and b also has to be less than 1. So since b is positive, it has to be between 0 and 1. So like 0.5 or 2/3 or something like that. We say that a logistic growth function in terms of x is a function that can be written in the form f of x equals c over 1 plus a times b to the x. But remember, this is an exponential function, and we have 2 forms we could write that in. One where we use any generic value b, and one where we choose the value of b to be that natural base e. So these are equivalent forms, just depending on how you've written your exponential part. We call c the limit to growth. I guess I should underline that. That's like a definition. And we say that if b is positive or is greater than 1, or if the k is negative, then we call this a logistic decay function. So it's just, there's two types in the definition. So if this b value is between 0 and 1, it's growth. And if it's bigger than 1, it's decay. Now notice that's opposite as for the exponential function. The reason it's opposite is because, well, the b is in the denominator here. So a big number in the denominator of a fraction is going to make a small fraction. That's why it's kind of reversed. And the same thing with the k's. So here, notice that when the k is positive, it's growth. And when the k is negative, it's decay. And you're probably wondering, why isn't it flipped? Well, it's because we snuck this negative sign in on k so that the k's actually behave the same way. It's one of the advantages of this kind of form for an exponential function is you can make the logistic match up so the k's are describing kind of the same thing. So let's talk about end behaviors now for this. So logistics actually have two different end behaviors. So if I talk about the limit as x approaches negative infinity, so I'm plugging a very small number in for x, like negative 1 million. What that's going to make is the fraction a over b to the 1 million. Now that b to the 1 million is going to be like an enormous number. So when you have a fraction, we have a number on top and a gigantic number on the bottom. That fraction basically goes to 0. So really what we'd be left with is just 1 plus or 1 over c. So we'd say that that's c. And what's going to happen if that value for x goes to a big positive number? So a times a big positive number is just going to be another big positive number. And 1 plus a big positive number is still a giant positive number. So we have the fraction where we have a normal, like a regular number on top and a gigantic number on the bottom. What does that fraction go to? Becomes 0. So we actually have two horizontal asymptotes, one at 0 and one at k. So let's just graph one of these on our calculator and kind of see what they look like. Or maybe we'll graph a couple on our calculator to kind of see what they look like. So this first one we're going to graph is 10 over 1 plus 3 times 0.6 to the x. And then just for grins, after that we'll graph a second one. That'll be 31 over 1 plus 4e to the negative 2x. Okay. So, gonna go back to our y equals. Gonna clear out everything that was in there before. And when I like to do this, I like to use the fraction option. So I'll press alpha y equals and choose that improper fraction option, the very first one. I'll just type this in exactly as it's written. It's 3 times 0.6 to the x. Okay. So in terms of choosing a window, I know that my horizontal asymptotes are going to be 10 and 0. So that'll help me choose my y min and my y max. And then my x's, I can pick any real number for x. So I'm just going to go like negative 10 to positive 10. And then I know my y's are going to give me my horizontal asymptote, so we'll do that. And so there's my logistic that's kind of bounded in between those two. And let's actually go and like maybe make this a little bit wider. Maybe we'll go negative 20 to 20 just so we can really kind of see what's going on. So you don't see anything. The reason you don't see anything is it's like right on the x-axis. It's very, 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 very close. But you get this kind of like stepped on letter S kind of curve. An S curve is sometimes what we'll refer to those as. Okay. So just turn that guy off because I'm not sure if we're going to do anything else with it. I haven't decided yet. And we'll just type in the other example. So that's 31 over 1 plus 4 times e. To get the e option, I press second and then the ln button right there. And we'll do negative 2x. Okay. And then we'll go to our window. So what I need to change now is that my c here is 31, so that y max should match the c. And we'll keep everything else the same. So you notice here that this was much steeper, but we still have that same kind of S curve. If you're having trouble seeing that, I'm going to press second and zoom and just turn the axes off real quick. It'll be easier to kind of see what's going on. So there's my logistic curve. Very steep as opposed to the other one. Let's graph the other one on the same axes here real quick. So I'll do that and it'll be easy to see which one is which because of the thickness of the line. Oops, if I remember to turn it on. So if I press enter on the equal sign, I can turn that function on or off from graphing. Okay, so there's the other one coming in. You know, not nearly as steep in the middle there, right? So those are what the graphs of these logistic functions look like. So things that we might be interested in would be like maybe finding points on these things. So to find a point on this, all I'm going to do is like pick a value for x and plug it into my function. So for example, if I wanted, say, f of 0, I would just do alpha y equals, and I'll just do 10 over 1 plus 3 times 0.6 to the 0. Oops, forgot my plus sign there. All right, and when I do that, I get 2.5. So there's a point on that curve, 0, 2.5. So no big deal. Now, you might ask, like, why should we care about these exponential or these logistic growth or decay models? Well, if you think about the sorts of things we described exponential growth or decay being good for, one of them was like population, right? And if you think about it, a population usually doesn't just grow and grow and grow and grow and grow. It'll eventually get to like a steady state where there's not any more resources and we just kind of reach a maximum carrying capacity or whatever, and the population really stops growing. And a logistic model, because of that second horizontal asymptote kind of creating a ceiling for the growth, really provides a nice description for that sort of situation. So let's look at another example here of a population where we're going to use a logistic model. Okay, in this example, we say the population of a city can be modeled using this logistic growth equation. P of t, we chose P for population and T for time, is equal to 1,425,397 all over 1 plus 21.783 times e to the negative 0.04982t, where p is the population after, or t years after 1950. And we're asked at the beginning of what year will the city population have 1 million. So this is a situation where I know I'm going to have to round this up to the next whole number when I do this. We're lucky here in that we got our logistic model just kind of given to us in the problem. So to solve this, all I'm going to do is clear out the stuff that's in there. And I'm going to type in that logistic model into one of my y's. Here I'm going to use y1 in my case. And then I'm in the other y spot. In my case, I'm going to use y2. I'm going to type in the 1 million that we're looking for. And then we can just find the intersection. Okay. Now, before we do this, though, we're going to have to reset our window, because remember, we typically have to do this each time we want to solve by graphing. So again, the x is going to represent the t in my equation, which is the time. So the minimum time we can have is 0. And then we want the years after 1950. Well, we don't really know what the starting population is going to be like. So we can't tell or how fast it's really going. So it's just kind of a stab in the dark. I'm just going to pick 100 because, well, I don't really know. That should be big enough to capture it. And really all I need on my window is it just has to be good enough to where I can see the intersection. As long as I can see the intersection, I'm fine. For the y-min, I'm going to use 0 because, again, I know that's one of the asymptotes. That's the floor. And then for the y-max, I'm going to use my other asymptote, which is c. So that's 1,425,000, yada, yada, yada. In the interest of just using round numbers, I'm going to use 100 or 1.5 million, just because it's a nicer round number. It should be, I don't know, I'm just partial to them. You could type that whole thing in there, but. Okay, so here is my logistic curve. There's 1 million. And you'll notice that I forgot to turn the axes back on. I'm going to do that real quick before I forget. And I'm really confused when I try to graph something a little bit later. So there's my axes. There's my logistic curve. There's my 1 million. So there's my intersection. So this is a good graph. Again, if you pick your window, all you need to be able to see is the intersection. It doesn't matter the rest of it. Now you're often going to be able to kind of common sense out what a good window might look like. But if you have to take 2 or 3 tries to kind of get that intersection, that's okay. All you really need is the intersection to happen. We'll do second trace, pick the intersect command. And again, I only have 2 curves, so the first curve is one of them, second curve is the other, and there's only one intersection, so I can just press enter again on the guess. So that happens at 79.002. Years after 1950. So it's asking at the beginning of what year. So 1950 plus that 79.002 is 2029.002. So that means at the start of 2029, population wasn't 1 million. So that's not going to be until 2030, the next year, where the population exceeds 1 million, right? The population gets to 1 million right after the start of 2029. So the first year, or the beginning of what year, the population exceeds 1 million, well, that doesn't happen until 2030, and we just miss it by a hair. So that's it for this first section. It was a doozy. Good luck with the assignment. what I'd like for you guys to do is what I'd like you guys to do is 1 through 16 from the problem set. Okay, good luck, and we'll see you guys next time.